With the knowledge of the Christoffel symbols, we can tackle the question, what are the components of the derivative of a vector field expressed in terms of these varying tangent basis vectors? If we express a vector field V as a linear combination of the tangent basis vectors, we write this as VA times EA. Taking the derivative of this with respect to chi b, we find dB times VA EA, and using the product rule for derivatives, this is equal to EA dB VA plus VA dB EA. We will rename the summation index A in the first term to C. This is just a change in what we call a summation index and does not affect the expression itself. Doing this and using the Christoffel symbols to express dB EA, we find that this is equal to EC multiplied by dB VC plus VA times gamma BAC. We denote the expression within the parentheses here as nabla B VC, which is called the covariant derivative of the vector field component VC. And these are the components of the derivative in the b direction of the vector, which in general, since the basis changes from point to point, is not going to be the same thing as the change in the components. Instead, the first term here is due to the change in V due to the change in the components VC, whereas the second term is due to the change in the basis vectors themselves. We can also follow exactly the same argument for the covariant components. If you write V as a linear combination of dual basis vectors and differentiate with respect to chi b, we find that this is equal to EC multiplied by dB VC minus gamma BCA VA, which is the covariant derivative in the b direction of the covariant components of V. Summarizing, we find that the covariant derivative in the b direction of the contravariant components VC is equal to dB VC plus gamma BAC VA, and the covariant derivative in the chi b direction of the covariant components VC is equal to dB VC minus gamma BCA VA.